I would like to thank the Architecture Foundation for the opportunity of joining this fantastic initiative. And in saying good evening to everyone and trying to be as inclusive as possible, I also wanted to highlight the power of accessing data with my first slide. So in this case, it took me only a few seconds to collate 87 different ways of saying good evening in many different languages. But these slides also show two other important aspects of working with data. The first is the trust of data sets. So I haven't checked that every word is correct. And this is sometimes a problem when dealing with large data. And the second one is data bias. So 3 different words here are highlighted. One is my language, one is the one we speak, and the other one is my wife's language. So, obviously I'm biased while looking at these data sets, and data bias is also a very important issue to tackle. Back to me for a few more seconds. I've been very lucky to be at the right place at the right time when I joined AKT2 back in 2007. While the studio was designing iconic projects such as Hyder Aliyev Center with Zaha Hadid, and subsequently, for example, DK Pavilion with Thomas Erwick. These are my all-time favorites. And with my team, I've been very privileged to be part of many larger design teams, meeting amazing people, and also learning many skills while delivering truly amazing pieces of engineering. So the thing that really stuck with me, though, the most was having to deliver this engineering project was the impact that data knowledge and manipulation can have on the final design. In this conversation tonight, we'll cover a few important lessons I've learned using some of our completed projects and researches to hopefully help the discussion. So the common denominator that unites us tonight is perhaps a shared curiosity on how technology and data are transforming our industry. And hopefully there'll be an interesting debate at the end of the evening, although I wish someone could set up a virtual pub because I really miss the post-lecture drinks and nibbles. But anyway, so technology really has already changed the way in which we move, we interact with people. We actually proven it right now more than any other time before. The way in which we eat and we live. And it also changed the way in which we understand the world around us. And so through real-time data interpretation, like in this research where some people visualize the pulse of New York City population heart rates, getting them from their devices. This diagram is very, very powerful because it shows to me, many layers. It shows us density, it shows us stress, it shows occupancy, resource consumption, only in one data set. Without data, we wouldn't be able to understand the existence of some problems, such as climate change. But also we wouldn't be able to track and potentially adjust some other problems, such as how different countries, for example, right now are trying to flatten the curve of confirmed cases of COVID-19. So having the ability of plotting real-time data really allows us to understand problems, but also trying to tackle them straight away. It also allows us to see how some problems are affecting other problems by projecting the data using existing predictive models, such in this diagram where it shows the impact that the virus could have on people at risk of starvation. But also even just informative data sets are very, very useful to get inspiration for design. And this is taken from one of my favorite websites. It's called visualcapitalist.com. They publish every day very, very interesting visualization of large data sets, and I really, really recommend it. So before going through the detail of some examples, I thought let's give a little bit of thought in what generates these shifts in usage of data and how they might impact our industry. Obviously, under the engineering perspective, the data sets are linked to technology and to computing power. And there are 3 major laws that actually are ruling technology innovation. The first one is Creator's Law, which is basically telling that disk drive density, or in small words, storage, and it doubles every 13 months. So storage increase. Moore's law, perhaps the most famous, tells us that the number of transistors doubles every 3 years. So there's a performance increase every 2 years. And obviously this impacts the time. We can do stuff a lot quicker. And the third one, perhaps the less known, is Neesons Law, which tells us the bandwidth available grows 50% every year. And this is the possibility of sharing data. So the fact that now we are being able to share in video and presentation, and later on with 5G, we could share other things. So this law, basically, these three laws allows us to also look at, predicting what comes next. So back in 2012, we were predicting that augmented reality, NFC payments, speech recognitions, media tablets were gonna come, and the iPad was launched straight after that. But now, for example, we can look at what's coming next. And these are Gartner diagrams. They're very, very spot on most of the times. So in the next few years, we will see, obviously, explainable AI, which will make a big impact. Autonomous driving, a big impact in sort of transportation, and many other discoveries that will come forward. Sometimes prediction and projection, though, can be disrupted. And this is a big limitation of data analysis. The inability of basically predicting future changes. For example, in 1944, Freeman Ryder estimated that the Yale Library will have 200 million volumes by 2040. And based on that data, they calculated that uni libraries were to double their sizes every 16 years. We obviously know that that didn't happen, because with the PDFs and computer storage, people are using books a lot less. So two of the biggest disruption we could see in the near future that might have the ability of disrupting these systems are the opportunity of store data in living cells, which obviously the big impact, or the big sort of a problem right now is how to store data is that we need data centers, and they're quite large and expensive. And obviously quantum computing, which then will speed up the power of calculation of computing and to a different level. Before going through some practical examples, I thought it would be worth to summarize also some challenges of working with big data. The first two, is obviously structuring and manipulating large data sets and visualize and interpret data. They're very, up there. So I just took a slide as an example. This is a study done in a city of Sicily. People have mapped large data sets of basically the reaching, the time for people to go from point A to B, using different means of transportation, walking, bicycle, car sharing, and things like that. And obviously then they had to compress all this data, plotted up on a system that would actually make use of the actual data set in the background, and also removing bias. And I think this allows us to think just a little bit on what skills we might require to do this, to these operations. So we need new skills. We need software developers. We need data engineers, gaming developer, perhaps, that help us visualizing and interacting with these data sets. Also, we need new tools. We need, interoperable software, database solutions, cloud storage, and cloud computing. Large data sets are quite expensive in terms of storage. So it's a bit of an infrastructural change that we might have to face to be able to use these systems at their most challenge, let's say. So the third and one of the most interesting things as well for me, as I try to introduce in my initial slide, is the bias, is how to remove bias though. And there's many type of bias in statistical analysis and data analysis, but I think one of the most interesting ones is survivorship bias. And there's just a funny story to contextualize it and to explain it. And it's regarding falling cats. So there was a study written in 1987 about cats falling out of buildings, and it stated that the cats who fell from higher stories have fewer injuries than cats who fell from lower down. This was very odd. So they explained the phenomenon using terminal velocity, which basically means that cats falling from higher than 6 stories reach the maximum velocity during the fall, so they start to relax and prepare to land, which is why they don't injure themselves so badly. So 10 years after this theory was completely disrupted, because some other research pointed out that in fact the cats who fell from higher than 6 stories might have had a higher chance of dying, and therefore not to be reported to the veterinarian. So they were simply not registered and didn't become part of the study. And the cats who fell from higher but survived were simply falling more likely. So it's really interesting on how to analyze different type of biases and trying to remove them from our research, let's say. And lastly, obviously, the verification of the data sets and the future proofing, it's very tricky. And for those interested, I'll point out a very good book, The Flow of Averages by Sam Savage. And one of the best quotes to me is that the best models using in predicting data shifts are the models you no longer need, because they have changed the way you think. So I guess one of the questions that we might just ask ourselves tonight is, can big data influence our industry? So I thought, first of all, maybe let's have a look at other industries, how big data is already influencing other industries already. For example, agriculture. There's a large use of data sets and data-driven sort of crop assessment. This is an example of John Deere, applications which allow farmers to look and in real time their crops, looking at their machines in real time, their efficiency, what's going off, what's going wrong. It's all live and interconnected, and basically it's improving efficiency of crops. Or even in other industries, in the consumer and retail industry, this is the Ocado, one of the Ocado terminals for shipment of products. Obviously, these with interconnected, real-time positioned robots, Ocado is managing to track their shipments and to prepare the shipments by fully automating and using robots instead of humans, which obviously compressed the storage requirements. It's speeding up the time, and it's got a lot of different other benefits. But for us, obviously, being designers, it's not about improving something that is repetitive and it's trial and tested. It's trying to improve design, which we all know has got so many parameters around it, so many people, so many players. And so let's have a look a little bit on how maybe data can help us in the design. I will introduce some of the projects that we've delivered in AKT using the systems, and but just to introduce what affects design on our perspective. To me, there are those 5 different categories. So the way in which materiality affects behavior, the way in which behavior then affects geometry, and then subsequently geometry affects performance and performance affects comfort. And this is like a recursive process throughout the design that we have to try to manipulate and trying to get external information in the process. So big data and understanding of data impacted a lot materiality. Nowadays, we are able to go a lot more in depth into materials. For example, this is a microscopic shot of concrete. So trying to understand how the material behaves, especially when it fails. Data is helping quite a lot because we can access a lot more in-depth data sets and understanding relationships of patterns and behaviors. This is another shot of the same scale of steel. So we can actually starting to recognize patterns of failure and understanding why this thing happens. And in a way, we are then learning how, new way of designing and enhanced method of manufacture will make our materials stronger, lighter, and more effective. Looking at timber as well, we're learning a whole lot of more lessons from this material, which is heterogeneous. So by being able to assess a lot more in depth the performance and categorize the different types of timbers, the different performances against different loads, we're learning a lot more on how to use it in our buildings and to how to sort of optimizing the use and, and reducing the wastage, for example, and things like that. And glass equally has had, in the past 5 years, has seen an incredible mutation in terms of structural, environmental, and aesthetic performance. And all this development was pushed not even by our industry, but was pushed from Silicon Valley. So companies that relies a lot on data, such Apple and Google and a lot of other ones, have seen the potential of actually tapping into our industry and trying to push it on that side, which is quite interesting. So the formal research that we pushed at AKT in the past few years and applied to many other buildings consisted in linking, for example, materiality to behavior. In one of those projects we delivered with Zaha did, for example, looking at performance of concrete shells, we actually combined, the performance of concrete to the behavior and changing the parameters of the shell. We've been able to assess, what would be the optimal, conformation and the optimal material concentration in the shell. But for example, we also link how behavior affects materiality in reverse. In this case, we looked at how seismic actions would impact the glass skew on this large glazed dome. And we could tailor the material and the performance to different specifications. So we could see that the top seismic action and the bottom are the same, but with different structural parameters, the two structures behave completely differently. So again, dealing with large data sets here allows us to understand the impact of one action to the other. But also how behavior affects geometry. This is a project with Bjarke Ingels in Norway. He's looking at a museum bridge spanning over a river. So very, very initial study here. We looked at how the behaviors, in this case, the behavior due to the actual position of the supports affects the geometry. And similarly, how geometry affects performance in this study of how, varying the outriggers of a tower can help us reducing the displacement and therefore, improving the performance of the core. Also, performance affects comfort somehow. So we have developed tools, which I will show later on, that allows us to understand the impact of our changes in design in comfort, which is also one of the aspects that we're trying to maximize in our designs usually. So in terms of very, very quickly spending a couple of words on research. Usually research is an exercise that look at the past, where you're looking at understanding a specific problem through analysis. So you start from a hypothesis and you go through historical data to converge to a solution, but also look at future. And that's where the creative side comes in. So be able to synthesize his current data sets and create a solution that hasn't been solved before or written before. And the combination of those two things is what excites us, and in AKT and the project we're delivering, and especially in my team, the research that we're pushing forward spans over many different disciplines, and therefore focuses on computation methods applied on design, and looking at developing interoperable tools that connects architecture, engineering, environmental design, and fabrication, because we obviously we cannot do this on our own, and lots of the parameters that we are willing to change resides in other realms, so we need to kind of work together. And to that respect, we've been spending some time developing an internal workflow that allows us to connect the different softwares as well that we use throughout the design to facilitate this process, not to spend too much time into dealing with modeling and getting the right parameters in the models, but actually to focus on design, which is the most important to us. So we've been sort of pioneering this approach early on in 2008, where we're already looking at, for example, designing footbridges. This is for a competition for a footbridge in Farringdon, where we were using people flow to define the width and the depth of the bridge. So we're predicting how many people would actually go on the bridge to then specify the actual geometrical and the structural parameters. And further later on in the sort of higher relief, instead manipulating actual geometrical data and trying to optimize the panelization of the system. So trying to assess along the design the different families of the panels. Obviously back then it was quite an expensive process to procure molds for different cladding panels. So it was imperative to understand what could we change in terms of geometry to rationalize these panels without losing the grace and the beauty of the architectural layout. So we had to manipulate this data and trying to understand a lot more from it. So we scripted this internal solution to extract the information from the data that we had available. So a lot of it's about geometry, and I took a small example on Bloomberg headquarters, and not in the whole project, but essentially in the central part of the project, the main architectural ramp, because this was a very early example on how we connected those different data sets, different parameters, and how we work together with the architectural studio to drive the process of design. So the whole ramp is based on one sort of mathematical function. It's called a hypotrochoid curve. And we use this function in our software to generate the actual the model of the ramp. So to be able to manipulate as we go along, and as the design kind of changed, to be able to manipulate that geometry was essential for us then to be able to respond to the changes of the design. The ramp is also actually connected only on 3 points, which made it quite lively. So the biggest problem, engineering-wise, was the vibration. And this is where we actually really, one of the first examples when we realized the power of data. By extracting all these parameters and working together with the architects manipulating the design change, we actually managed to extract the vibration plots very, very quickly out of the very complex model. And we realized a very, very interesting behavior, which we never actually had experienced before in staircases, as a matter of fact. And which was basically the impact of a person walking on the top flight at a peak of vibration in one of the bottom on the bottom areas, which we would normally not expect in this type of structure. And we've been able to highlight this only by managing to run very, very large data sets and to then visualize back the impact of these data sets on the actual structure itself. So, I thought it was a very relevant sort of examples on how data can actually help us designing in a better way, so understanding a lot more the problem. These are a couple of shots of the actual ramp coming up in the construction. Sorry, I think my computer went a bit. Yeah, so another example is Merchant Square Bridge with Knight Architects in Paddington. This was very interesting because obviously being a relatively small footbridge, but the interesting part is that this is a movable structure, so it's got some dynamic associated to it. There are 5 fins opening and closing to allow the barges to go through. Quite nice and elegant. And the ambition here was to trying to keep this ratio of very, very slender fingers. So the challenge was for us to define an optimal combination of different parameters, such as the position of the piston, the position of the pivot of the bridge, and the size of the counterweight, to be able to actually use a very small equipment to fit within the mechanical area, but still to comply with the loading criteria, especially in the movement configuration. So we did actually run quite a lot of models trying to see the impact of varying the counterweight and the position of the piston and the pivot, trying to interlink all these different parameters and trying to extract the data that was important for us, which was actually the sort of the balance of all of the loadings. So again, another example on how tipping into sort of different data sets can allow us to modify our design to comply with the parameters of the design, let's say. And these are a couple of more shots of the bridge. Another interesting one to me was the Serpentine, because this one opened up a different level of data assessment. So the Serpentine, if you've seen it, was based on a very, very simple generation of the surface. The bricks confining all of the structure were mapped on the surface. So a very, very regular, distribution of geometries. But basically, the interesting part of this is that the whole process was driven by one algorithm that we've set up together with Bjarke Ingels architects. And this was to actually being able to maintain the very strict time requirements of the competition, but also to trying to understand the impact of using a material that was never used at this scale on the fabrication. So we had very, very limited time to assess the GFRP material that actually was defining the boxes. And we had to then basically get some of the boxes tested outside in the university and remap the results of those tests back into our models to verify the design. So the whole algorithm was actually built to be able to do this exercise, where in the part on the left, the geometry was controlled by Bjarke Ingels architects, and the part in the middle we were creating on the different iteration, different global and local models that we needed for the design of the structure. And then on the part of the right, we're compressing all these results into the production phase. So for the beam modeling, if you want. And so we've been able to actually constantly varying the geometry and understanding where the distribution of the forces would be carried by the different connection, and then quickly then having the ability to communicate in real time the areas or the boxes that had some connection failing, and therefore to allow the design team to reassess the geometry. But the second benefit was also, as I said before, to being able to study the behavior at 2 different scales and to validate the design, that was actually coming back from the results of the tests in the university. So the results of the test then were used to calibrate our structural models. And when we actually compared what we were predicting in our analytical model and how instead the real test was performing, we actually then had quite a moment of reassurance where our data was verified, so we could progress with the design. This was mainly to prove that this material could be used at that scale, to prove to the authorities that were questioning us if that was safe. And obviously, not being codified before, we had to go and down to this route, and therefore producing a lot more proof, let's say, in that sense. But definitely, having this approach of open sourceness, allowed us to really communicate back and forth to the architectural team the different kind of performances of the different solution, and try a lot more options, on the design side. So these are some shots of while it was being built and while it was kind of assembled, I think back in 2016. So the other aspect obviously is performance. In our industry, big data has already influenced progress and advancing materiality and performance. But one of the best things that we are kind of discovering is the ability of actually using real life or real-time sensors to assess performance, which takes us to the next step of designing not with code, but with design, based on performance. This is one of the towers we recently completed in South London. There's a summary, obviously, of the parameters that we've been using throughout, obviously, our analytical side. So the actual, this is all digitally produced. We actually partnered in a research with the University of Bristol, Mace, and another company called Gas Dynamics to actually use live sensors and to assess then the performance of the real building, and to then look at if the predictive models that we use during the design phase could have a corroboration in the real life. So we went on and purchased our own sensors, anemometers to look at direction and speed of winds, and accelerometers to understand the impact on the sort of response spectrum of the tower. And we actually have installed on several stories of the tower, and we let them capture data for about 6 months. And we are now in the phase of post-processing the data, and we will compare it to the analytical models that we have to understand the impact of simulated versus real life performance, in the hope that this will actually allow us to obviously have a different set of parameters while designing. And I think this is the most exciting sort of part of our work and our research, being able to really understand how the structure behave in real life. And another side of it is very important, obviously, is comfort, which is all interlinked. We started looking at comfort several years ago. This was a shopping mall in Turkey, which was badly affected by the wind get trapped and captured by the high rise recently built, and was actually projected in the atrium of the shopping center, creating a lot of discomfort in the people visiting the area. This actually pushed us in trying to develop a toolkit to assess comfort, not only in the perspective of wind, but also under the lens of solar and thermal comfort, to be able to inject in our design at a very early stage, but also during later stages, with a different set of parameters that allows us to understand the behavior of our designs a lot more in depth, in a lot of different scales, from master plan to building and to envelope. And I think it's really important to start to look at these features while we're designing. So we actually created an automatic sort of system that allows us to assess wind speeds and then get the impact of those onto the comfort levels at pedestrian level. So in order, again, to facilitate the design phases and to have an influence, for example, on the massing or on the orientation of our designs. This data set, which is very, very large, gets mapped and used to and post-processed to understand the effect of on wind comfort. So there's a a recognized scale that allows us to understand if some areas are within acceptable criteria versus not acceptable. And while we are doing these exercises, and we do several of them around the UK, but also internationally, we're starting to gather a lot of data and basically mapping the behavior of our buildings within the context of our cities. So all those areas that you see in pink are areas where we actually already performed quite a detailed analysis, so we know a lot more on the comfort levels on these areas. So I guess that one of the examples that actually summarizes all these different approaches is the tide, with Night Dragon and the Scofidio in the Greenwich Peninsula, where we combine all these different capabilities, the ability of manipulating geometry, the ability of actually understanding different manipulation of the geometry, the impact on the structure, the impact of the performance, and the comfort generated by wind. So in this case, we set up, a very interesting series of models that allows us to understand, the changes in the proposed scheme, also in context of looking at the future master plan, for example, and the impact of some changes that we would have to do, the impact on comfort, but also the understanding of how sort of geometry will impact on performance. So in this case, those bridges are very, very slender, and to be able to maintain the slenderness, it was not enough to come up with a structural system that was stiff enough to avoid large vibrations. So we had to kind of study the structure a little bit more in depth, and breaking down the fabrication parts in order for us then to manipulate the material where it was mostly needed, but also understand the performance criteria we were designing into. And so by running a lot more detailed models that allowed us to capture the impact of different paces, of different people, different configuration of people walking on the walkway, allowed us to then really extract all these data sets, map them on the geometry, and understanding how people moving across the walkway was impacting vibration. And we soon realized that to keep the geometry quite slender, we had to rely on additional measures outside the actual material. So we had to actually implement a system called tune mass damper, which it's basically a weight on a series of springs that counteracts the impact of some people walking or running onto the structure, and therefore limits the vibration of the structure. So basically interlinking all these parameters together allows us to really push the boundaries in terms of design, maintaining the aspiration of the architects and the slenderness of the structure. And this was all basically enabled by having access to large performance data sets and combine them together and trying to find sort of lines of of understanding, let's say, throughout those. But manipulating data is not only useful in complex applications. We're currently developing an internal database that allows us to browse through our existing projects and compare different solutions employed to inform the next challenges. For example, the ability of understanding, in different projects how our floor sandwich compares, or how manipulating grids on areas or materials impacts our buildings. or in more interesting as well, understanding, in terms of reuse, how buildings were built, and can we actually reuse some of the resiliency in those buildings due to the fact that the loading criteria are changed. So we have a lot lighter sort of requirements. So can we actually, use this power and look at how, without having to drastically change the context of our buildings, can we, for example, reuse some of the structure? Can we add floors? And what's the impact of adding different materials or different loading on top of these existing buildings? Definitely, quite a useful thing to do. Very, very quickly, last five minutes on current research. So in terms of data-driven design, we are looking at the next level. And this research actually looked at how we could sort of use algorithmic design and robotic fabrication to let the computer design sort of their own structure. So we looked at a very simple floor plate where the algorithm only assesses the design to understand where the loads are going, basically, and where the impacts of the load is going. This data is sent to the robot, and the robot basically translates a deflection parameter, so how much the structure is moving, into a carving movement. So if the structure moves too much, the carving is less. And if the structure moves little, the robot carves more. And so this is actually in an effort of actually reducing material in our floor plates, but also designing sort of geometry within, without us having to input that parameter in. So the actual robot translates the data and has his own interpretation of it. It's very, very exciting. We are trying to get to a point where we can test this on a concrete plate, which is also quite amazing. This is one of the earlier examples. We just used a foam panel just to test the motion of the robot. And other applications also in terms of accessing large data sets. This is an exercise we did with mod architects and looking at drone spraying. And the interesting thing here in data is that the drone positioning and the jet of spraying of this sort of composite natural material on top of those shells was controlled by artificial intelligence. So the drone is actually reassessing its position every time using a camera, and is then regulating the jet of the actual material on top of the surface to be able to cover the majority of the surface. So again, very, very interesting thing, using a very resilient and natural material as well, which was quite nice. We did this for the Milan Design Festival last year. And very quickly, the last example, we did have a go on understanding how then manipulating data in real world could be achieved using AR and VR and mixed realities. So for the London Festival of Architecture last year, we looked at the opportunity of mapping some live data sets on our mobiles to give people the ability of actually understanding a lot more about the city hidden boundaries, in order to also see if there's a possibility of having a participatory design tool. So in this example, the app would allow users to visualize in real space through their camera, visualize, for example, the wind performance around some buildings, how wind is actually affecting our environment, or visualizing air pollution straight from the sensors available in London. We mapped air pollution in any part of London, telling people, for example, if they were in an area where the actual concentration was dangerous or not. And also giving users the ability of actually casting a vote, which we just did it for the fun of it back then, but also to understand if actually it's possible. So we did give people the ability of actually casting a vote in relation to their location, a positive or a negative vote under architecture, public or environmental criteria. And actually we saw a very good response. which is very, very interesting. We were receiving a lot of data in our servers from users, and this was actually the first day of launching of the app. We started to receive a lot of those votes, for example, which allowed us to start to see how people perceives our cities and perceive the design or the comfort or the or the constraints of our cities, which we thought was very, very interesting in the lens of actually using those tools in the future for allowing us to design. I'll leave it to here. I think I hopefully have a few more minutes for questions or a debate, and I'll leave it with a sentence that kind of, I was just looking at a YouTube video the other day, and there was a paid advertisement of these design masterclasses from Hungary, and he says, if you know what you're going to do in advance, then you won't do it. So I guess that currently, in our industry, there are many software companies that are trying to advocate perfect solution to optimize designs, but what they really offer, they are very constrained systems where the creativity is hindered. And so we should really focus a lot more in understanding the spaces and the processing of the data for benefiting our real design, and not letting a predefined solution affect ourselves. So I'll leave it to this. I hope you enjoyed the talk, and if there's any question, I'm happy to answer.
Thank you so much, Edoardo. That was really great. Thank you. Yeah, if there is any questions, please pitch them in the chat. It's now open to the public. But firstly, I wanted to ask how, like, when you're working with data sets, how you see this might become a kind of influence in an architecture that responds to climate emergency, and how that's kind of how you're working in that aspect.
Yeah, so it's we are currently developing our take on an assessment of, for example, the impact of our material usage on the, obviously, on things like carbon, and but also cost, and the relationship of those parameters together. The work that we are doing in the background is really trying to come up with a very lightweight database system that allows us to browse to the different parameters of the project that we are currently designing or designed in the past, to allow us to make those relationships together. So the trick here is to really push on coding and those skills that I was mentioning at the beginning, trying to find custom solutions and not to rely on predefined ones, because large data sets are hiding a lot of useful information, but if we're not able to browse them through and to clean them properly, they also could create wrong and skewed answers.
Mm-hmm. How are you? I guess I don't have any questions yet, but I'm kind of interested to know more about how, when you're working with architects, the kind of working relationship with the structural engineer and an architect, and how you find that they adapt to using data sets as a driver of design.
I think at the moment, I think we're very lucky. In the past 10 years, I think we've seen a major revolution, and there's the basically digital era already. So you can see there are a lot of architectural studios, even small ones, which we collaborate with. They're really keen on mapping those different data sets in their designs. And our approach is always trying to kind of to sort of be participatory, and trying to really use the technology and the positive sides of technology as much as possible to facilitate the conversation. So we use those tools in trying to really have a discussion in the design meeting to see, okay, how this particular data set influences your design, and vice versa. We're really keen on understanding also from the architectural studios their perspective. But I think we're really lucky and in a very privileged position to be able to work with a lot of different architects which have shared that passion with us.
Mm-hmm. I think if you just unshare your screen for a second, and then I think we have a question from Francesca, but her microphone isn't working, so I'm just going to read it out for you. So she's wondering if there are reliable open source software to experiment with data as an architecture student.
Yeah, so the open source repositories, I think they're available. There are very many, and there are actually, I think London has got a very good repository that allows you to basically extract their data sets, london.gov, I think, london.data. I don't think there are softwares per se, but I think the best coding language to use to start with, at least, is definitely Python, because there's a lot of libraries in Python that allows you to do data mapping or data statistical mapping. And so there are predefined solution in the Python language that allows you to do this operation. So if you, from one side, you source your data from these repositories, and on the other side, you use a good computer language that's got pre-made solutions, you can combine the two and quite soon get your own interpretation on your data sets.
Okay, well, I think we will wrap up there, but thank you so much for such an interesting lecture. Next in the program, we have Christoph Graf, who will be presenting some of the research that in his book, People's Palaces. That's at 7 o'clock. And then tonight at 9 p.m. we have Matthew Vanderfield, who is the producer of the interview podcast series called Scaffold. So I'm going to unmute everyone for a round of applause, and yeah, good night, everyone.